Yeah, thanks. Welcome back from lunch. I think the almost last session of the day. My name is Dennis Thielke. I'm part of the Cloud Native team at Microsoft. I've been around pretty much the last 3 years when we started Kubernetes. Pretty much that was when we kind of figured out that their service fabric isn't actually the only game in town in terms of microservices. Anybody here running service fabric? No, you wouldn't. Good. So the talk I want to do today is basically about kind of what are the typical questions when you're adapting Kubernetes. What are the things you need to get started? So typical questions everybody sees kind of how to start with the basics. Then how can I get a clusters up and running? How can I build and release, deploy applications into this? Having solved the deployment problem, the next question typically comes about kind of how do I get insights into what the stuff I'm changing has an impact on. So is there a new bug? Is the new version better than the last one I did before? So rolling updates every couple of minutes doesn't really help if you're not able to see the difference. The next part typically is about scaling. I think we had already talked about this earlier. So just want to introduce kind of our perspective on this and the contributions we're having in this space. And the last part, which is typically the first thing we talk about when we talk about Kubernetes in enterprise, is kind of security, because everybody is kind of really much comfortable with using infrastructure-based applications, perimeter security. How to adapt that kind of to cloud-native world where we actually have to secure applications and not so much the infrastructure. And yes, hopefully there's a little bit of time at the end to do Q&A, but I will be after around anyway, so no rush there. Good. Next part is kind of always remember why we're doing this, right? The objective is not to run infrastructure, to upgrade, run tests, to run deployments. We want to drive value and deliver continuous value to users. And that kind of means that there's also a process component in space. So not about kind of buying the best technology, but also changing maybe the way how we work. And that is pretty much also an interesting motivation, kind of why we started with Kubernetes in the first place, right? Kubernetes has started because people started using containers, and containers to do at scale is actually very hard. And this is why we came up with Kubernetes, or at least Google came up with Kubernetes. In that sense, because this running containers at scale is really, really hard. Especially kind of the problems, security, automation, logging, monitoring, all these little things that can slow you down. And Kubernetes seems to offer a couple of answers to this, but at least a couple of other ones, and I want to show you the difference that is required to get there. So that's sort of the first part. Containers are the source of problems. How do we deal with them in an efficient way? So containers can be cool stuff to run, but you have to get from source code to containers in some form in an easy way. And what we've seen in the beginning is kind of people started running container-based builds on their local machines, which is a bad idea because you have creating a dependency between your local infrastructure, your local Docker engine, and you're running artifacts that you're shipping later on. The next worst thing you can do is running builds inside clusters. Because the easy thinking is kind of, I already have this sort of this containerized environment, and why can't I use my existing Kubernetes clusters to run application builds or container builds? But then again, it solves the same problem. First of all, you're creating a horrible security risk, kind of introducing the capability to build containers inside a Kubernetes cluster, cause a lot of follow-up issues. This is why Containerd has limited the option of building in a containerized cluster. And you shouldn't kind of, if you're starting fresh, you shouldn't even go there. So think about, I need to build containers, but I wouldn't never do it either locally because it kind of introduces a management hassle. And if I run my builds in Kubernetes, in my production clusters, I create a huge security risk. So where do I build my containers? And this is why we're kind of, you might have heard that there is an initiative called the Container CBI, Container Builder Interface, which is sort of a general interface that is supported by all major hyperscalers, Azure, AWS, and also Google, in which you can outsource the responsibility of building containers. And this is kind of, sorry, CBI should be for anyone, maybe not the central browser of investigation. I didn't know that this was a container builder interface. That's the one you will look for. Essentially an open source project that allows you to do this. And what this gives you is an implementation. So it gives you an interface that is standard, so you can move around, you want to not want to be tied to a specific vendor, but you want to get a service that does the implementation of this. And with our case, you can see here that there's the Azure Container Registry, which essentially is doing the same thing. It is building containers as a service for you. You throw a bunch of source code and a Docker file, set of Docker files added, and you get back and build image. And how does it look like in Azure? So anybody familiar with the Cloud Shell? Sort of is also container-based runtime where you can pretty much get all your tools that you need to build and run applications. Also has Visual Studio Code, which is quite handsome because you want to typically also get your, not that I want to advocate this as a very good environment. Let's start this one, close, is it still running? Don't save, sorry. Assuming you have kind of a bunch of container-based applications and you want to run a simple, very primitive Docker image in there, you can move into this and simply ask kind of, dear Microsoft, please build that service with the code that I've been running in my GitHub in this case, or any kind of other resource control. Please trigger a build task and build the latest code that is in there. You can see that there's what I did before, because there's obviously something required to deal with authentication. Not everybody should access your source code, but also anybody should access your registry. So therefore, I have to do a little bit of plumbing here to do this. But after I have that done and covered, I can go in and say, please build me a new image, and make sure that the piece of source code I have somewhere in my registry gets turned into a running image that I can run somewhere else. And the base idea here is not only about individual containers that you're running, but also think about the base dependencies. Because there are two ways why you need a new container. First of all, because the code has changed, and the other reason is because your base image changed. Think about the patching and the containerized world is upgrading the base image that you're depending from. And this kind of creates very quickly a kind of change. So in this case, I'm moving from a base image that is kind of, first of all, quite old, but also built from Docker Hub, but in most enterprises, you typically build from your own base image. And then kind of you have to synchronize this kind of way in which the operators bring a new base image, and the developers need to be notified to trigger a new build. And this is why the service that, in this case, is implementing the service, and which is the other Azure Container Registry, is offering, first of all, a build of a containerized application, which just happened. So I can see here that there has been new build a new container that should be somewhere around here. That can be triggered by myself, by source code changes, or by because the operator that built the base image that I'm depending on has built a new release, and therefore required all my depending images to be rebuilt as well. And that kind of, all these things are encapsulated in this interface to make sure that you have kind of abstracted and solved that problem for now. Let's put it this way. Good. The other part is that this also needs to be accompanied with the way how you bundle your application. I think there was also discussion earlier about how to packaging and release applications. I think a little bit disagree with the fact that an operator should be used for deployments. So Helm is actually a package manager, in that sense, for maintaining and composing dependencies of your application. And that also has a very tight integration. So think about containers are the base element of how you compose your applications, and Helm sort of being the Klammer, in German, for lack of the English word, the Klammer around the individual applications to make that work. And this is why you can, in this case, in the container registry, not only store your images, but also use it as a Helm repository to list and see what is going on inside this specific container registry. So because in this case, looking back at the application that we just talked, I've now built an application. Now I want to check, first of all, sorry, this was the one long view. I want to take a look at what kind of applications in there. So in this case, just a demo application, but you can see next to my container images, also my Helm package repository is encapsulated in the same registry because they go together, right? Because they access to, they're both tied to the same lifecycle management. I version my containers, I also version my Helm charts. And I also need to integrate them with security because not everybody should be able to push images or Helm packages And the same way goes kind of pulling images as well. So role-based access control around all these things abstracts all the problems you have around life-cycling applications and the Helm charts that go along. The next part you might have heard that we announced last year with Docker and together is kind of the Cloud Application Bundle. So packing not only the things that you have here in Registry and picking that up and shipping it to maybe disconnected Kubernetes clusters. Think about Kubernetes for submarines or Kubernetes for cruise ships, which is something that actually is happening today, where you need to encapsulate all the dependencies, the base images, the Helm charts, and the underlying configuration pieces and ship it to somewhere place that is completely disconnected and has maybe even doesn't have an internet. So taking this a little bit further, and that kind of requires bundling, packaging, and all these tools together. So I think it's better, right? Good. So now that we've solved the issue of kind of building images, we need to talk about the bigger thing. So I'm not sure if you've already seen this. Helm has sort of created this very nice curated marketplace in which a lot of open source projects are now contributing stuff. So I think looking at so it has usually had a very small scroll bar, but you can see there's tons of stuff in there which people are already creating applications. Think about this as your marketplace and sort of like an app store for an enterprise in which you can pull down curated applications that are being maintained in a distributed way and kind of think about your enterprise environment. Your Kubernetes cluster is now being the next thing to your marketplace, right? This is the marketplace. You want to pull applications down, upgrade them, run them from there. And that makes a lot of sense. Looking at the cluster in this case, oh, sorry, clicked on a link somewhere. If I now look what is going on my cluster, I can see that there's a lot of stuff going in there. I can run this to install applications from my registry, from the public marketplace, upgrade them, and have them versioned, probably tagged so they can roll back and forth between what I've done there. Some of these things are going to change in Helm 3, but while we're waiting for the architectural changes that Helm is currently undergoing, this is currently the way we go there. Good. So now we solved this. The next part is kind of how do I get a cluster up and running? So I've found a way how to package and release applications. Also in the way how I can build containerized applications. Just curious if you're interested in, we've also created quite a bit of samples for different languages, different frameworks, in which we kind of generate kind of proper Docker files with multi-stage builds, not the crappy thing I showed you earlier. And also Helm charts that are being generated by VS Code or also by Draft, which is a tool that we're integrating in the open source space, which you can use to create both Docker files and the Helm charts that go along with that. If you want to get started in Azure, the typical way is that you start with something that we call a DevOps project, because it does exactly give you a playground in which all of these things are started and solved from default. So essentially you go in and say kind of, yes, I want to do DevOps. And since I'm in Azure anyway, this is something like a template generator. So it goes through a couple of questions. You can see there's not only .NET in there, that time has passed. Think about the stuff that you wouldn't have seen here, kind of think about Java. You go in and say, yes, I like Spring, maybe, that's nice. And I want to do Kubernetes, cool. You give it a name, you ask it to spin up a cluster or use an existing cluster. And after that's kind of been doing a bit of rumbling, you will end up getting something that looks like, let me check, this looks like this, which essentially creates a CI/CD pipeline inside a Git repository that is maybe on GitHub or on your own configured Git store. You get a build pipeline that builds, so take a look at this. The build pipeline that goes in and say, I want to do certain things, like I want to build the containers that are in there. I want to package a Helm chart. I want to put that Helm chart into a repository. And I also want to get a release pipeline that allows me to make sure that whatever the artifacts I'm creating here can be packaged and deployed to a cluster right away. Kind of using Helm, using the packages and a bunch of tooling in between to make sure that you're kind of starting up right up front. So if you want to get started actually, so you have a language or you have code already configured, I think that would be the easiest way to get started, because it will get you the tooling, the the infrastructure you need. So you can see that there's a Kubernetes cluster being created. There's also a container registry being created, and what we call application insights, which is kind of stuff for analyzing telemetry, which you can kind of start right away for any language. And so you don't have to start from scratch. The next part is kind of that most people typically not only have a little bit more requirements on how they spin up Kubernetes, right? So at the beginning, when we introduced AKS last year as a managed service, essentially kind of offering you an API service for Kubernetes, which simplifies a lot of the operational aspects to basically saying you have an API, the blue one, you can talk to this API, and the rest of the infrastructure is managed by us, upgraded, and made sure that stuff doesn't break away. And in the experience, that looks like this: kind of go in, say, oh, I want a cluster, and get a couple of questions: which version stuff, which data center, how big, spin it up. Please give me some authentication into my out of directory, something I will talk later on when we talk about how to secure not only infrastructure but applications. There are a couple of network decisions that are typically not that easy, and kind of yes, please, I want a bit of logging and monitoring as well, and spin it up and running. The way how we separate that, because essentially Kubernetes is an open source technology that we're not changing. So right, we're taking open source upstream Kubernetes, packaging it up, and deploying it as a service, is by another open source project that we're using to stamp out templated environments. So think about when you're talking to Azure, that's kind of, there's an API behind this, and you're asked, please give me a Kubernetes cluster. What we're actually running under the hood is a project called AKS Engine. AKS Engine is sort of the mechanism how we can stamp out sets of individual clusters with a lot more configuration options that you can see here. And the AKS service essentially is using the AKS Engine tooling underneath to stamp out individual environments that consist of compute, networking, and a bunch of Helm charts in addition to that, to make sure that the application is kind of is running and can be managed. And the interesting part for customers is actually that they while they obviously cannot modify the AKS service, they can very much contribute and change the behavior in which we stamp out environments. And that changes stuff like feature flagging of the masters, that changes certain kind of security configurations, service mesh integration, and a bunch of other authentication tools that can be plugged into the service to make sure that there's extensibility for open source technologies that is out there, right? So obviously we have to kind of take care about the service that we are running as under SLA, which we take responsibility, while giving you a little bit more flexibility, and the AKS Engine is actually exactly that. So this is why a couple of customers actually contributing, merging pull requests into the AKS Engine, and we're releasing every Monday, assuming that your check-in is stable. You will be able to benefit in your existing and new clusters very shortly after the check-in has been merged. Now good, so having solved the problem of getting an AKS cluster up and running, it looks a bit like, let me check those in the right cluster. I think, so running Kubernetes infrastructure, I think, shouldn't be that interesting to you in this case here, because it essentially says kind of you have an API that is running under a dedicated URL. You have a little bit of options, kind of say, I want to get a new Kubernetes version. In this case, I'm on the latest version, so there's nothing to do. And I can kind of scale clusters and say, yes, I have a little bit more nodes capacity in there. That is essentially it. While the other part is dealing with the fact that you also want to get some insights, right? While you do not get access to the underlying infrastructure on the masters, you have kind of the need to look into logs for controller or scheduler, because there might be stuff that's going wrong that you cannot change, but at least you want to get the logs out there. And this is how we can get you access here as well. So we integrated a bit of tooling which gives you an overview of kind of the cluster view, the node, the controller, and the individual containers, which you can grab the logs, say kind of, yes, please say there must be something that, maybe there is something that does generate a little bit of logs. And so that I can get maybe let's do that later, a bit of logs in here to see all the overview. And since Kubernetes is sort of advertised and not as a kind of infrastructure orchestrator for whole data centers, more like an application project resource, you will end up having lots of clusters, right? So think about, in this case, I'm running a very small application set. I have 6 clusters running. You can see that Microsoft is sort of configured to take responsibility of 3 of them. One is completely unmanaged, and the other one is kind of sort of on an unknown state because I haven't configured it here. Which gives you kind of the option to do fleet application management, because at the end you want to look at, there's a set of infrastructure running. How are, first of all, the overall cluster status? How the nodes, meaning the parts that my application is running on? What are my user pods, which in this case is resembling your applications that are running in there? And how are the system pods, like core DNS kind of stuff, kubeproxy that are required to keep the infrastructure running, so that you have an even view. Is everything green? Am I happy? Are my customers happy and able to interact with that application? Good. Going over a little bit closer into getting insights into the individual applications, I typically am not satisfied with seeing green bars, because I mean the application can be running and still producing a lot of nonsense, not working. In this sense, I want to show you some fancy, high sophisticated application, obviously, that I've built by myself, which is calculating prime numbers in a very complicated fashion. So essentially, this is a completely nice microservice-y built application that has kind of an Angular front end. It has a couple of backends, has a cache and a Redis cache in front, and a backend that is doing the prime number calculation, one in Go and one is doing this in JavaScript. So maximum complexity for a very simple application, but having the necessity to have multiple parts that are moving can be updated at the same time. Looking at this, if something goes wrong here in the user space, there might not be an easy way to figure out what the problem here is, because it looks from user like an API that I call into. If I trigger something that we call, and this is part of the Azure DevOps project by default, is called Application Insights, which essentially is modifying your application dependency. So pulling in another logger that is listing on standard out and standard error, and forwarding all the logs that it's seeing into kind of a central stream source. And it's also doing something quite interesting, because it's adding correlation tokens between service-to-service communications. Think about different microservices, front-end calling is the back-end. I need to be able to correlate the calls from the front-end that coming in from the JavaScript front-end to the back-end. And therefore, it's also doing a little bit of correlation to make sure that you're able to understand and reason about the dependencies in the communication paths here. And what this does is, at the end, hopefully that works. My application has been running, so let's check. So you can see my application consists of a couple of front ends, a couple of back ends, actually not that many, and my so I think there is the last hour, so let me just add the numbers, because I did a couple of scale operations. And what this service was able to do is figure out that this is kind of how my application topology looks like, right? It hasn't received any kind of information about how my application works. It just was able to correlate the requests that are being piped in, and seeing that there's some local Redis cache running in front, which also is connected to 2 instances of the front end and 3 instances of a backend service. There's some JavaScript-based front-end application running that is also receiving telemetry here. And now I can dig in and figure out, for example, which Redis cache queries are the slowest, having an impact on the front-end query. And this thing is completely versioned. So think about you're upgrading this application every day, providing new versions, and you're kind of modifying the Redis query. This gives you kind of a version histogram to differentiate and compare the results in terms of performance and capabilities of your application as you're plugging up and changing stuff on the run. I think that can be quite sophisticated in solving this. Obviously, there's a bit of drawback here. The other alternative how you can do something like this is introducing a service mesh, which has a lot of operational complexity to run and introduce correctly, while this kind of is doing the compromise of changing a little bit of your packages, dependencies, and for your kind of Node or JavaScript or Java application to make sure that the telemetry is correctly forwarded. I think it's an interesting case. It also gives you a little bit of insights into the application, and you practically don't have to run any infrastructure to make this work. Good. The next part, and this is something that I couldn't get running, unfortunately, is doing debugging in production applications. So think about, again, same scenario. I have a kind of application, in this case 3 tiers. There's a front end, there's a kind of middle. My API is sort of the API me as Scott that I'm currently developing. And I'm depending sort of on service C, which is something, again, I don't know who actually running on, who is building it. But you can assume that there are at least 3 developers, each of them updating continuously an application or part of the service. And we're running, and since you can only do correct microservice debugging and testing in a kind of sort of real environment, we're using a development environment, development cluster in this case. So everybody, we're running in the same cluster. The problem now is, how do we work correctly being able to upgrade stuff without interfering with each other? Think about, I'm Scott, I want to test the new version, the pink version of my web API. Dave is sitting here developing service C, and if we're trying to build and debug an application, so actually setting breakpoints inside my web app, hitting that web app from remote, I don't want to see the breakpoints from Dave as he's developing service C, right? So there needs to be some magic in here. And this is something that we've been doing, essentially an extension as Envoy underneath, in which we can deploy a sidecar proxy into all of these services. We're adding also a little bit of telemetry to figure out that if a user is coming in from this DNS name, that it shouldn't be, and it's in this case me, Scott, the traffic from web frontend to MapIO APIs should only be routed to my instance, meaning my pink instance. And this gives me the option to set breakpoints here, doing this in the same space, and Dave and Steve can do this as well in the same environment. So it's I think a very powerful capability to debug this and run this. And this kind of works in any Kubernetes cluster. Obviously, you can turn it on in Azure by default if you want it. It's also not designed for production, so you never should debug in production anyway, but just to make sure that this is not the sort of kind of thing that you would have in production, because it's obviously messing with your routing quite significantly, and it's purely for debugging and gaining insight, not so much about kind of getting logs or analyzing production environments. But it's a fun thing. Unfortunately, I couldn't get my demo environment running. But if you want to set up, it's called Azure Dev Spaces. You can spin it up, and if you spend a bit more time, you can even run it outside of Azure. Good. So next base is the scaling of applications, right? The correct balancing of infrastructure is very hard to do. So in this kind of being a very simple case, you have 4 dedicated nodes. There's almost no chance in which you're able to run an infrastructure that doesn't produce any waste in Kubernetes, because Kubernetes was never designed to run, actually was designed to run on VMs, and that means you never have actually the ability to size your cluster correctly. You're either having too few capacity, which means you're wasting money, or you have kind of overcommitted, which means your application probably has issues. And something that we started 2 years ago is the virtual kubelet, which essentially is a connector that you can plug into the Kubernetes control plane, which makes and turns Kubernetes from a infrastructure orchestrator to a pod orchestrator. And that has quite a couple of interesting aspects, because essentially, if you think about the terminology, what you actually want to do, you want to run applications that are based on containers. You don't want to run infrastructure or VMs. This kind of just came sort of as a package deal, because 5 years ago, there was really no other option to run infrastructure distributed. You needed VMs to run on. With the virtual kubelet, that thing has changed, and that is sort of gives you a couple of nice ideas in how to connect this. So let me connect you to my is that readable from the back? So just make sure. I think there's a bit of issues in the networking today, but that shouldn't. And I'm also in the wrong cluster. Let me fix that. Because I was moving. That is actually the right cluster. To show you how, okay, so very good, and let's do that same thing again. What you can see here is that my cluster sort of consists of 3 actual proper nodes, and there is this sort of virtual node that has been attached to the control plane. And that the nice thing about this, that this virtual node essentially has affinity capacity. So affinity actually means currently we have a default limit of 800 pods you can schedule there on this node of infinite capacity. And the nice thing about this is that this is tied to Azure Container Instances, which is a service that can start a container within seconds. So a VM typically takes a couple of minutes to start up, being correctly tied on the infrastructure. It needs a boot core DNS and a bunch of other daemon sets that you don't actually want. But they're also wasting your capacity. In this case, we're kind of tying in this virtual API that is able to provide you essentially unlimited capacity to connect into your cluster and spin up new pods as you need them. And to show that a bit of on a demo, I've built some, think about this is sort of the Black Friday on a very popular shop. So if you know Contoso, it's a very good customer of ours. They buy all our crap, even the lazy MP3 players. And they're running a kind of sale, right? So there are hundreds of people jumping onto the site, or about to jump onto the site. And I'm simulating this by running a little bit of load generator in here. So kind of make sure that this website will be nailed with a couple of requests. I should be actually already running. Let me also start Grafana to take a little bit look into how that works. So hopefully that should be all right. So what you can see here, essentially, this is kind of the request per second. These are the number of instances, right? So this is kind of how my current capacity looks like. I only have 2 instances. I'm probably under capacity as I need them. And as the requests go up, I can see now that the kind of typical Kubernetes architecture, or in this case the autoscaler, kicks in and detects, the number of traffic is going up. And you can see it's already spinning up new pods of my online store, which are going up quite quickly. So this gives me essentially infinity capacity, and it's a bit careful in the marketing terms, that are being spun up as the load goes up, and ensure that the application in here can accommodate the load that is in here. And the nice thing about that is, first of all, that the Azure Container Instances that are now being spun up in my, let's show you my Azure infrastructure page, which we haven't talked about so far. It is I think this one. Exactly, you can see the container instances, which is essentially just pods that are spun up by Microsoft. There's no infrastructure underneath. It's running completely disconnected and tied into the cluster. These things are cheaper than VM. You can size them by capacity exactly as you need them. So if you have the pod spec that requires this thing to have 8 GB of RAM, this is exactly what you pay for. And you're paying for the gigabyte seconds that you're actually using as compute. And these things are cheaper than VM, so it's quite attractive to use this instead of actual virtual machines in your underlying infrastructure. So is that refreshing? Okay, it's refreshing. So you can see the scale operation is happening, and as I put more load onto this, you can see that here this is kind of the total requests. Total requests going down. Why are they going down? So probably I don't know, it's still working. But the important thing is that the average rounded request per containers is going down as the number of instances increases. So these things actually behave in terms of the Kubernetes API like any other pod. They have health probes, they are integrated in load balancer, route robbing, all these nice things. But they don't have infrastructure underneath. And that has, from our perspective, is the next interesting thing in cloud native land, to make sure that we're actually getting rid of VMs or virtual machines underneath the infrastructure, so we're only talking about containers. Good point. So now we'll talk about scaling. 2 things that I want to show you, because security, as mentioned, is also quite relevant we're dealing with this quite a lot, is the different security aspects. And Kubernetes looks for typical operations teams quite scary, because you have a lot of endpoints that you need to secure. There's the API server you need to lock down. There's a thing called pod security policy and network policy, which is not that easy to handle today, I would say. And you also need a way to kind of manage not only individual infrastructure, but applications. And something that I want to show you here just quickly is something that we launched last year is giving a pod an identity. So in Azure, as you might know, we're not using connection strings to authenticate to databases and stuff, but we're using Azure Active Directory, so giving delegated permissions from a infrastructure to another piece of infrastructure, both having strong identity, and there's no need to kind of to share credentials and put them into environment variables because these things will never be secure anyway. And that idea, what we obviously could have done from the beginning is giving your cluster an identity and giving every application that's running inside the cluster the authentication to authenticate to a database, for example. But there has a bit of a problem in multi-tenancy. Think about you having a lot of applications running inside your cluster. You don't want to give every application the permissions to authenticate a database, just the application one in there. And something that we built here is called an AAD pod identity, which means a pod effectively gets a unique identity depending on the spec. That says, let me give a sample here. So it's based actually in a custom resource definition. And in this custom resource definition, the important part that you want to look up is here. I'm giving it a binding. This binding says that this application that is running as part of this deployment has been tied to this identity in my Azure Active Directory. So there's a couple of daemon sets underneath to make the plumbing work. But the cool part about this is that giving you the sample of showing the demo. This is a pod that is running here that is now authenticating, in this case, to a key vault. The secret that is being used to authenticate to this key vault that is storing all my super secret stuff is not persisted either in the configuration, in the environment variables, or on disk anywhere. So it's kind of really on-demand authentication that's happening here. And this application is thereby authenticated to access a secret that is part of my key vault in here. And I think that's also quite an important step to kind of limit the attack surface. You only can see kind of the number of requests, so there has been obviously enough successful authentication, and I also can look at the application later and show you, if you're interested, in how that works. But the essentially cool thing about this is that we're now talking about application-based authentication, no longer about infrastructure-based application authentication or credentials and secrets, which will make cloud-based application at scale quite messy. And the other thing that is also maybe quite relevant is policy and compliance. So this is kind of part of the open policy agent called Gatekeeper, which is something that we open sourced, or actually we're using internally for 2 years now, because we essentially have the problem we're running 100,000 clusters, right? And we want to keep certain kind of applications inside the cluster. Like this is kind of stuff that you might have seen in, if you're looking inside, I actually have to shut down because otherwise it will be quite expensive. You can see yeah, that was a good point. If you look inside an AKS cluster, there are a couple of extra pods that are not by default. So there are Kubernetes-based not part of upstream Kubernetes, but we still need them to keep your cluster up and running. And if you try to mess with them, try to change the configuration maps or stuff, the cluster will revert back to the original state. And this is something where we're using with the open policy agent, which gives us the option to keep certain kind of compliance-based parameters and configuration settings inside the cluster and prevent users or developers from messing with them. And for us, that means we want to keep these applications in your cluster that we're sort of reporting telemetry back and forth, but you can also use that. And a couple of use cases that might be, you might recognize as well is, I want to, for example, prevent people from creating public IPs, right? If you create a service, put a load balancer and it's a spec, you will get a public IP. A lot of companies don't like that. Most of them want to have a private IP, but you sort of cannot prevent people from doing that. You can do it on the permission level of the infrastructure components, but it's kind of messy because it breaks a lot of stuff. Or you can use the open policy agent, which is sort of evaluating the request. Kind of think about this is the YAML developer throws in. The open policy agent goes in and changes this specification into a private IP address, which means developer can write as he wants, but effectively is only getting a private IP address. The other thing is kind of that is quite common is you want to prevent people from using registries that are not compliant. Just to give you a little bit of idea how this looks like. This is sort of how a policy looks like. And And this policy kind of prevents people from pulling containers from an image that you're not that you haven't whitelisted, right? It's kind of a matter of authentication, but you kind of sort of cannot prevent people from pulling images from Docker Hub. With this kind of policy, you can, and this is also a mechanism that you can use to govern aspects of large case deployments, because we have customers running thousands of clusters, and for them kind of going into individual clusters is really not possible anymore. They have to use these kind of policies to define well-defined parameters in which an application or a set of applications can run. And I think that's a cool idea how this can be done. We're using it internally, and it's undergoing a couple of infrastructure and architecture changes. So I wouldn't recommend to use it in production today, at least not this version. But I think it will, going forward, have a couple of interesting solutions in there. In terms of timing, we're almost out. So just, are we not? No? Okay, good. Network policies, typical thing. I don't think it's that special. Calico seems to be the way to go here. We're supporting that as well as an Azure native one. And the only difference being here that people when it comes to firewalling between applications, most of them want to have their own, want to get support. So we want to choke someone if something breaks. And maybe it's better to be us if you're running infrastructure anyway. To close that, if you want to see demo stuff, you can pull this off my GitHub if you want to. Otherwise, if you want to get started, use the Azure DevOps project. I think it's a cool way to start because you get all the things I just show you out of the box and in a meaningful way. And I don't think a meaningful way to ask questions now. Maybe we can. Otherwise, thank you very much.